All right, so now we're going to jump into capacitance. And capacitance, the core idea of capacitance is when we have two metal surfaces, any charge added on them will create an electric field between them. So, for example, if I put charges on, say, something here, positive charges here, and if I put negative charges here, there's, of course, going to be an electric field that points from positive to negative charges like that. Okay, so no matter how the surface, they don't have to be flat, they don't have to be in general. So there's and because there's an electric field, and we talked about before, there's a electric field is also given by this negative, the magnitude of the electric field is the rate of change of the potential, change in potential divided by the distance. Oops, and there's a negative sign technically there. Okay, because of that. That means if there's an electric field here, then there's also a potential difference between here and here, between those 2 points, right? And so the relationship, there's a linear relationship between the charge and the potential, and it's governed by this Q equals CV, where C is, we call the capacitance. And the units of capacitance, if you think of this formula here, this is going to be coulombs is equal to C times volts. So this unit here is going to be coulombs divided by volts, which we call a farad. Okay. Now, the other thing is there's potential energy that is stored on a capacitor, because to make that charge configuration required work to do it. And so the overall potential energy is also given by 1/2 QV or 1/2 CV squared. If you plug CV into there, you get 1/2 CV squared. So again, this is a shorthand. Rather than summing up a bunch of charges and adding up the equation for potential for every pair of point charges, right? We just say capacitance allows you to find a way to find the potential energy of that entire charge configuration very easily. Okay, now the most common kind of capacitor we study in AP Physics 2 is going to be the parallel plate capacitor. And this is the most basic capacitor. It has 2 parallel plates. They don't have to necessarily be rectangular, but they're big in area. And we assume they're very, very large compared to the thickness between them. Now, technically, the electric field, so like if the positive charges are in here, like this, and the negative charges are down here, then the electric field kind of points from top to bottom like here. Technically, in the edge, we call these fringing fields. Technically, the electric field is going to go like this near the edges, but we typically ignore that. That's why we assume sometimes they're very large, but if you think of like the electric field, we call this fringing fields, by the way. And if they're small capacitors, you do have to consider them. But in general, we assume in AP Physics C or 2 that the plates are very, 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 very large compared to the separation. So we don't usually worry for that. So for 2 parallel plates, if you're given, there's a couple of formulas here. Is that the capacitance is given by epsilon naught A over D, where A is the area of the plate, and D is the distance separating them. And epsilon naught is just a constant. I don't remember the constant value. It's a constant, though. Okay, and you can look at the vacuum permittivity. The electric field is also given by the potential difference divided by the distance. And if you remember this, right, this negative change in potential over this, you just say, well, the distance is D, the change in potential. It turns out that it is actually just straight up this ratio here, even though it's not true for any other parallel plate capacitor. And for those of you in AP Physics C, we'll derive this using Gauss's law. But for those of you in AP Physics 2, just know that it is uniform. One thing to keep in mind is the electric field is the same everywhere. No matter how close you are to the top or bottom plate, it is the same everywhere. Kind of seems a little weird that that's the case, but it turns out even if you might feel like, oh, I'm closer to the positive charge, isn't the electric field kind of bigger? Well, that might be true, but what happens is the electric field then like points from the various charges. There's some that are pointing down, right? But from the positive charges pointing away. And then the negative charges, like this negative charge, this negative charge, this negative charge, it's pointing more vertically. So even though it's further away, they're tending to point a little bit more vertically. So the end result is it doesn't actually matter where you are vertically in this distance. The electric field is the same, no matter if you're closer to one plate or another. And that's a really important fact for parallel plate capacitors. Okay, so let's do a few example problems just to understand how this works. We have plates of an empty parallel plate capacitor as a capacitance of this and are too far apart. What's the area of the plate? So again, we use a C is equal to epsilon naught A over d, and you wanted to solve the area for the plate, so it's going to be C times d over epsilon naught is equal to A. And then you're just going to plug in the numbers. 5 times 10 to the negative 12 times the distance, which is 2 times 10 to the negative 3. And then let's look up that vacuum permittivity because I don't have it memorized. It's 8.85 times 10 to the negative 12. And so you do that. You get your units that are going to be in square meters, whatever number you get here, using your calculator. Okay. When empty parallel plate capacitor is a capacitance of this, how much charge must there be on the plates for a potential difference of 100 volts? So here we're going to use two different formulas, Q equals CV, and this is epsilon naught A over D. Okay, so we want to know how much charge there is. So we need to know the capacitance. So we just plug that in, epsilon naught A over D times the potential difference. So this is 8.85 times 10 to the negative 12. What is the area? Oh, they didn't say the area. We'll say the area is just 0.25 square meters. We didn't actually say. It does matter. The separation is... oh, actually, I'm sorry. I don't know. They didn't... they just gave you the capacitance. So you're just using Q equals CV. Sorry. I was thinking parallel plate capacitor because they told us that. But they actually just told you the capacitance here on this one. So it's just 20 times 10 to the negative 6 times 100. And that's going to be, what, 20 times 10 to the negative 4 then. And that's going to be coulombs, or 2 times 10 to the negative 3 if you want. Okay, and that's it. That's kind of like just how you use those formulas. Oh, how much energy is stored. You can do 1/2 CV squared, or you can do 1/2 Q times V, because we have, it doesn't really matter. You get the same number. The Q is 20 times 10 to the negative 4, and then the voltage is 100 here. So then you would get 10 times 10 to the negative 2, or 0.1 joules, like that.